Hello again to another chemistry lesson. We are still busy with organic chemistry. We're going to be busy with it for a little while since it's quite a lot of topics. And we will look at the Lewis notation as part of the introduction to this course. So Lewis notation is a type of notation we use for covalent bonding. Remember, covalent means that we are sharing our valence electrons. Covalent, sharing valent. Okay, so with organic chemistry, we also said that organic chemistry is the chemistry involving carbon. Whenever carbon is involved in whatever covalent bonds, we are working with organic chemistry. So the most basic organic compound is called alkane. Well, they're called alkanes, and the most basic one is methane. Now, methane is a carbon. So in the previous video we watched, we looked at molecular formula. Molecular formula for methane is carbon with 4 hydrogens. Okay, now how does this work? Well, if we look at our periodic table, okay, we can see that carbon is in group 4. Now the group number tells me, the Roman numbers though, the group number tells me the number of valence electrons I have. So carbon has 4 valence electrons. Now in the Lewis notation, it's actually the Lewis dot. Okay, it's called the Lewis dot notation. What we do is we represent the valence electrons around the carbon symbol with little dots. So we've got carbon, and we see carbon has 4 valence electrons, so we go around adding those 4 valence electrons. Then we notice, then we go and find hydrogen. Okay, hydrogen we see is in group 1. That means he's got 1 valence electron, so he's going to share his valence electron with carbon. Okay, and the reason why they are going to share is because, remember, in a covalent bond, I'm trying to fill up my highest energy level with electrons. Okay, and that's exactly what is happening here. Carbon needs 4 more. You can see 1, 2, 3, 4 to be like neon. Okay, hydrogen only needs 1 more because his highest energy level can only take 2 electrons. So he just wants to be like helium. And helium has 2 valence electrons in his highest energy level. So what hydrogen is going to do is he's going to share, one hydrogen is going to share one of his only electron with 1 carbon. We'll have another one sharing with that one. We'll have another one sharing with that one, and then we will have another one sharing with that one. Now there's something called the octet rule. Okay, the octet rule it tells us that a substance is stable if they have filled up the highest energy level, and most of the elements need 8 in the highest energy level. So to test ourselves on whether we have a stable substance, we will count the number of valence electrons in around that element. Okay, so now we can see that carbon, since he's sharing some, he's got 2 here, and as soon as we've got 2 being shared, we can connect them with a line. We've got 2 there, so we've got 4, 2 there, so we've got 6, another 2, so we've got 8. Each of the hydrogens, we can also count theirs. They must fill up only to 2 though. So 2 for this one, 2 for that one, 2 for this one, 2 for that one. And this is the Lewis structure for methane. And don't worry so much about the name. You'll still learn how the names work. They're not difficult, but they are important. Okay, let's look at ethane. Okay, so ethane, the molecular formula is 2 carbons and 6 hydrogens. Sorry, not 3, 6. 6 hydrogens. Okay, so how does ethane connect all of these? Well, we've got 2 carbons Okay, and it is fairly certain that these carbons will always have at least one bond with one another. Okay, so the two carbons have bond. Now let's do it like this. We've got one carbon with 4. Okay, then we have another carbon also with 4, and this carbon will share at least one of his electrons with another carbon. And then when they share, we can connect it with a line. Then we have 6 hydrogens, so it makes sense to give 3 to each of these. So we've got one hydrogen with his valence, another hydrogen with his valence, another hydrogen with his valence. Okay, and so here also we have 3 here, all of them adding up to a total of 6 hydrogens. Okay, so I'm just going to connect all of these that's being shared again, and now we can go and count the number of valence electrons just to make sure that I have the correct number of valence electrons. We've got 2, 4, 6, 8. 8 around this carbon. How about this one? 2, 4, 6, 8 around this carbon. And if we check on the hydrogens, all of them will have the same number. Now let me quickly show you how to write the condensed structural formula. The condensed structural formula oh, that's completely spelled wrong, sorry. Condensed structural formula. Okay, we always start with carbon and then hydrogen. So carbon and hydrogen will come first. So what we'll see is that my first carbon has 3 hydrogens connected to it, and then I have another carbon with another 3 hydrogens connected to it. And it's as easy as that. We start with each carbon and describe first the number of hydrogens, then anything else, and then we'll move on to the next carbon with hydrogen and the rest will be in alphabetic order. Okay, then let's look at another example. Okay, let's look at butanol. Okay, butanol. Butanol has 4 carbons, okay, 1 oxygen and 6 hydrogens. Okay, so I should actually write it this way around. First hydrogen and then oxygen, 1 oxygen. This is the molecular formula. Molecular formula just tells me what atoms do I have in that structure. Okay, so we've got 1 carbon with 4 valence electrons, another carbon with 4 valence electrons, obviously sharing his one, another carbon with 4 valence electrons, okay, again sharing with this one, okay, and then another carbon with 4 valence electrons. So I've got 4 carbons, okay, and then I've got an oxygen. And our oxygen, if we go to our periodic table, you'll see oxygen is in group 6. That means oxygen has 6 valence electrons. Let's put him in a different color. So we've got oxygen. It's got 1, 2, 3, 4, 5, 6. So we can see some are already paired. Okay, and now we put in all of our hydrogens in all of the spaces where we only have 1 valence electron that needs a partner. So we've got a hydrogen here, okay, that's going to pair up, a hydrogen there that's going to pair up, hydrogen there that's going to pair up. Sorry, I said 6, I meant 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, sorry, I don't mean 6, 10. Okay, then hydrogen, 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 and then finally this one, we've got another hydrogen here, hydrogen connected to the 1 valence electron there. Okay, so these pairs we can also just connect with one another, and what do we notice? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Let's look at oxygen. 2, 2, 2, 2. So 4 2's again, 8. And all of the hydrogens must at least have one straight line representing 2 around it. Okay, or only have one straight line representing 2 around it. So let's write the condensed structural formula for this. Okay, we've got 1 carbon with 3 hydrogens. Then we've got another carbon. This one only has 2 hydrogens. Then we move on to the next carbon with 2 hydrogens. The next carbon has 2 hydrogens, and then we have an oxygen that has a hydrogen. Okay, so we won't write HO. Okay, and this specific one is a very special ion, the hydroxide ion. You would have encountered it in this course so far, so we will keep it as the hydroxide ion. It is one exception to the rule of alphabetic order, or the Hill system, where we start with carbon, then hydrogen, and then the rest alphabetically. This one will do the next element connected to carbon is oxygen that has 1 hydrogen. Okay, let's look at one more example. Actually, let's look at 2 more examples. Okay, in this example, I'll look at a double bond. Let's look at the double bond of propene. Okay, propene has 3 carbons. Okay. And it's got 6 hydrogens. So I want you to notice that here ethane had 2 carbons and 6 hydrogens. This one has 3 carbons and 6 hydrogens. What is happening here? Okay, so let me show you. We've got our 3 carbons with each of their 4 valence electrons. Another carbon with 4 valence electrons, and another carbon with 4 valence electrons. Okay, and now we only have 6 hydrogens. Okay, now my suggestion is that you try and make the number of hydrogens on the first and the last carbon the same. Okay, so since we have 6, we could give to this one 3 and to that one 3, but it's not going to work because the middle one also wants at least 1 hydrogen. Not always, but in this case we'll do it. Okay, so hydrogen here and a hydrogen here. Okay, then a hydrogen here and another hydrogen there. Okay. Now you'll see we have 1 more hydrogen left. Sorry, 2 more hydrogens left. Okay, so we could give a hydrogen to this one here, and we can give a hydrogen to this one here. Okay, and you will notice no matter how you try and structure it, there will always be 2 valence electrons that doesn't have a hydrogen to partner with, because obviously we had 1, 2, 3, 4, 5, 6, 7, 8 hydrogens that could fill this. Okay, in that case it would have be called a saturated hydrocarbon. Okay, which you will learn a little bit more about later. But what is going to happen in this case is that this valence electron here and that valence electron there will come together. They will form a bond by themselves. So instead of carbon just bonding once, it will have a double bond. We will have 2 bonds here, okay, because they didn't have hydrogens to bond to. So we will have a double bond in this case. Now, whenever we have a double bond, we'll start with that carbon. Okay, so in this case, we'll have a carbon. This double will go in this direction. So we'll start with a double bond, and we'll start with that carbon, and you'll notice that that carbon only has 2 hydrogens. Usually we had a carbon with 3 hydrogens. This one has a carbon with 2 hydrogens. Then I have a carbon with one hydrogen, and you'd see usually our middle carbons have two hydrogens, but obviously these two carbons are sharing a valence electron among themselves, so each of them are losing a hydrogen. And then finally we've got our carbon with three hydrogens as usual. Okay, so this is the condensed structural formula, where I just take each carbon and write all of the rest of the covalent bonds with it, starting with hydrogen. Let's do a final one. I'll make it an easy one so that we can finish this lesson. Let's go for ethine. Okay, so ethine is a triple bonded element, okay, which has two carbons. So we've got two carbons and only two hydrogens. You'd see usually two carbons will bond with 6 hydrogens. Each carbon would get 3, but in this case, okay, we have two carbons, okay, and only two hydrogens. Okay, and now you'll notice that we have all of these ones that don't have a valent partner. So these two will share with one another, and those two will share with one another to make a total of 3 bonds. 1, 2, 3. This is called a triple bond. Okay, and you will see the name for, or the condensed structural formula for this one is a carbon and a hydrogen connected to a carbon and a hydrogen. I think just as a last example, since it's not that difficult, let me add branching in here as well, and to show that, I will show you methyl propane. Okay, methyl propane looks like this. We've got 4 carbons, okay, and we have 10 hydrogens, okay, which is very similar to butane. Okay, butane has the same structure, but these 4 carbons are connected like this. We've got 3 carbons connected with one another, okay, and you'll learn later that's what pro means, is that we have our longest chain of carbons is 3 carbons connected with one another, okay, and the A means they're in single bonds, okay, and then the methyl means we have a branch, okay, a methyl means we have a branch, which means one of these carbons, and it can only be the middle one in this case, has another carbon connected to it, okay, another carbon connected to it, and so you can see the longest chain, no matter how you try and make a carbon chain, it's only 3, 1, 2, 3. While if I were to make this carbon chain, or this carbon here, okay, then I would have had a string of 4 carbons connected in single bonds. But here you can see this middle carbon is bonded not just to 2 carbons, but to 3 carbons. So this is called a branch. Okay, and now we can simply add up our 10 hydrogens to all of the remaining valence electrons. Okay. And there we go. That is not that difficult. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now let's just check our octet rule. We've got 2, 4, 6, 8 around this one, 2, 4, 6, 8 around this one, 2, 4, 6, 8 around that one, and then every hydrogen has a double bond itself. Not a double bond, sorry, double valence electrons itself. Okay, how would we write this structure? Okay, the condensed structural formula will again start with the carbon that is closest to the branch. Okay, just like in this one, we would have started with the carbon that is closest to the double bond. If there's a branch, we'll start with the carbon that's closest to the branch. And in this case, it doesn't matter whether we start at the back or at the front or the back of this structure, but we'll have the first carbon will have 3 hydrogens. Okay, so the second carbon, you'll notice, has only 1 hydrogen, but it also has a branch. Now, as soon as it has a branch, we put the branch in brackets, and that branch we will describe exactly the same as we would have any other organic compound. So we'll start with the carbon, and then it has 3 hydrogens, and that is it. Carbon with 3 hydrogens, and then we'll close our bracket and we'll continue with the rest. If there were any other carbons with branches as well, they'll also be represented exactly the same, but in this case we only have 1 carbon left with 3 hydrogens, and that is how we would represent the branching. Well, thank you very much for watching. I hope you learned something, and I'll see you in the next video.